Consider a population that contains two different alleles for a specific gene. The population is in Hardy-Weinberg equilibrium, and one of the alleles has a frequency of 0.3. So the first question asks us to calculate the frequency of all three genotypes in this population. So in other words, we need to calculate the frequency of the big A, the heterozygous one, and then little a. Okay, so the information that we're given really is just that we have a frequency of 0.3 for one of the alleles. So we can assign that to P. So P's frequency is going to be 0.3. And then recall that P plus Q, and both of those are representing the two different alleles, the frequency of those is going to equal 1. So if we know that P is 0.3, then really we're just solving for Q. And when we do that, Q is going to be equal to 0.7. Okay, so at this point now we have the frequency for two of the alleles. And it doesn't really matter which one you assign to each. So I'm going to put the frequency of the big A, that's going to be equal to P. So this is going to be 0.3. And the frequency of little a is going to be 0.7. And then knowing that information, we're going to be able to calculate the frequency of the different genotypes. So if we look at the Hardy-Weinberg equation, this would be it. So P squared plus 2PQ plus Q squared is going to be equal to 1. And I'll just remind you that P squared is the frequency of big A, that genotype. This is the frequency of the heterozygous ones, and this one over here is the frequency of the little a. So knowing this, if we want to solve for the frequency of this one, we would take P squared. And again, P squared, this is 0.3. So we're really going to do 0.3 squared, and that will give us the frequency of the heterozygous, the frequency of big A. If we want to solve this one, it would be 2 times whatever P is times whatever Q is. And then for the last one, it's going to be Q squared, which again is going to be 0.7 squared. And all that, if we added it up, we could double check and it should equal 1. So if we did 0.3 squared, that is equal to 0.09. If we did this, 2 times 0.3 times 0.7, that is equal to 0.49. And then if we did 0.7 squared, that is equal to 0.42. And so add those up and they should equal 1. Okay, so just to sum up what we've solved up here, the frequency of big A, that is this right here. So that is equal to 0.09, or you could say 9%. The frequency of the heterozygous is equal to this, so 0.49 or 49%. And the frequency of little a is equal to this, or 0.42 or 42%. To answer the next question, we're told that we've got 1,500 individuals in this population, and we want to know how many individuals have each one of those genotypes. So all we would do in this case is we would take our 1,500 individuals that we know we have, and we would multiply that by the frequency of that particular genotype. So for big A, it's 1,500 times the 0.09. When we do that, we're going to get 135 individuals. If we did this for the heterozygous ones, we'd take 1,500 times their frequency, which is 0.49. So that is equal to 735. And then for the little a, it's 1,500 times their frequency, which is 0.42, and that is equal to 630. If we wanted to just double check, we would add all these up and make sure they do sum up to 1,500.